Okay, so I think we'll get started. It is my pleasure to announce Victor Bloomfield, who's come to give us a tutorial on R. I actually am familiar with Dr. Bloomfield's work as a polymer physicist in biopolymers from when I was a postdoc and I was working in the same area. And Dr. Bloomfield has done a lot of pioneering work in hydrodynamic interactions and simulation of polymer systems, electrostatic interactions in DNA, and large polymer models of DNA. He has actually been most recently acting as the Associate Vice President for Public Engagement at the University of Minnesota, and also learning and teaching R. And in our group, we've had a very recent interest in picking up and learning R for porting some of our applications to this, really ubiquitous, powerful software tool which has a really large community behind it. And so I found this book on the internet, on Amazon.com. And I'm not sure I initially connected to Victor Bloomfield of this R book, but the Victor Bloomfield, whose papers I was reading when I was a postdoc. Turns out it's the same character. And I just out of the blue, I sent him an email and said, we're really having fun with your book, and we're making a lot of use out of it. Would you like to come out here and give us a seminar? And he agreed to do it. And so a lot of folks have the codes that he's going to, some of the scripts that he's going to be presenting, and you have them on a laptop computer. If you don't have a computer in the R script, you're welcome to sit next to me or somebody else who has a computer and look on, or you're welcome to just listen to the seminar and write some notes down. And we are recording this seminar so that we're going to post it on the web, so you'll be able to go back. Anything you missed, you can go back and look at the seminar and get more advice. So with that, Dr. Bloomfield.
Well, I want to thank Dan for inviting me and the rest of you for coming. And I've had a very interesting day talking with people about research they're doing and how R might serve their purposes. The chronology that Dan presented about my most recent career is lagged a little bit wrong. I'm, in fact, Professor Emeritus. I retired from all of my formal university duties in May of 2011. And to be frank, I thought, with some sadness and some relief, that I would never again be called upon to come visit another place and give a talk on something that I'm just a neophyte myself in learning about, as most of us are in the scientific talks that we give. But it's been a very pleasant day, and I've really enjoyed it. So let me give you a little bit of history before I start. As Dan noted, I sort of finished my formal career at a fairly high administrative level. Before that, I had, for 3 years, been Dean of the Graduate School at the University of Minnesota. And before that, I had a pretty active research career and balanced a lot of other faculty politics and associate dean of the graduate school and head of the department, all the standard stuff. When I turned 65, which was 8 years ago, I decided that I would, and that's when I became dean of the graduate school, I decided I would stop my, I wouldn't try to renew my NIH grant or my NSF grant, both of which I'd had more or less continuously over my career. I started at a time when we were very lucky compared to how things work now in terms of grant competitiveness. And for a few years then, for about 5 years, I was quite just sort of tied up with administrative things. Then I arranged a three-year phased retirement from my duties in the biochemistry department at the University of Minnesota. And my aim there was only to do one thing, which was to develop a course in computational biochemistry and biophysics. And so I started casting around, what's the vehicle I should use for this? And Mathematica and MATLAB were too expensive, and MATLAB doesn't run all that well on Macs without getting into the X11 system, or at least didn't back then. For spreadsheets, get cumbersome when you deal with large problems. And so I started looking around, and I'm not exactly sure how it happened, but I stumbled on R. And I think I was first attracted by the fact that its syntax, as you'll see, and the way of thinking, is pretty similar to MATLAB. I was probably even more attracted by the fact that R is open source and that it's free. And that means students don't have to buy it, universities don't have to buy site licenses for it. If we have students and postdocs from other countries, they may be able to afford through their institutions in the United States, but if they go back to Brazil or Vietnam or wherever, they're not going to be able to afford MATLAB or Mathematica there. And so having a free, powerful program to do scientific calculations, I think is very important. And as teachers and research supervisors, we ought to be very cognizant of this. And when we collaborate with people in other countries, or with people in this country at universities or colleges that are not well-to-do and maybe can't afford site licenses, using collectively a tool that is every bit as powerful, but is free, has major advantages for scientific communication. And so I, as you can probably tell from what I've been saying, I have a somewhat evangelistic attitude about these kinds of issues. And I make no apology for it. As Dan showed you, I wrote this book, which was basically to serve as a tool in a course whose main purpose was to teach biochemistry students, who are not notably quantitative heroes for the most part, how to do quantitative calculations in biochemistry and biophysics and molecular biology. And R sort of came along at the right time in my consciousness to serve as the tool. But R was not the main point of that book. When my 3 years of phased retirement ended a year and a half ago, and I thought to myself, what am I going to do with the rest of my life? I thought what the world really needs is a book on numerical methods using R. That is the kind of numerical methods book that has been written many times for many languages, using Fortran, using C, using Java, using MATLAB, using Mathematica. Let's do it using R. And so that's what I'm working on now. That's my retirement project. And we'll see how it goes. First draft is done. I've gotten some good feedback from the referees. Got a lot of work to do a second draft. What is R, for those of you who aren't familiar with it? It's a free software environment. Environment, I think, is the proper word, for programming and for statistical computing and for graphics. I mean, I think one of the really strong points is that it produces publication quality graphics with great ease. It's both an interactive environment, you can use it just as a calculator, and a programming language. And this third point I would really like to make a strong point of. It can serve as the basic quantitative, statistical, and graphic tools for most scientists and engineers throughout their careers. And I think one of the big failings that we have as an academic community is that we don't agree on a quantitative tool that we start using early in a student's scientific career and just keep going with. You know, we use spreadsheets usually for the simple stuff, and then maybe we go to MATLAB or something else later on, and every environment you're in, you use something different. And so, I mean, it's like any language, you forget how to use it if you don't develop facility with the syntax and the vocabulary and the grammar and so on. So I would push for picking something, and I think R is a good candidate, starting to teach it early, making students use it for their lab notebooks and everything else, and keep at it and use it, and then when you move to research, you keep using it. I would also point out that, you know, of course we want to do quantitative simulations and calculations. We want to present pretty graphs, informative graphs. Most scientists, I think it's fair to say, don't do nearly as much statistical work as they ought to. I did a survey of a few recent issues of Journal of Biological Chemistry, for example. Lineweaver-Burke plots, which is basically bad fits to linear data, and t-tests. There's hardly any other statistical approaches used in the biochemical literature, and the same is pretty much true of biophysics also. And R was developed, as we'll talk about a little more, as a language for doing an environment for doing statistics. And that is its real strength. It is the program of choice among professional statisticians. It is, I've seen it written, I have no way to assess the validity, that there are 2 million users of R. And I think 1,995,000 of them must be statisticians or students of statistics. Because there are not many people who are doing what I want to do and what Dan wants to do, which is to use R as a basic numerical methods language. But as scientists, we ought to be using statistics more than we do, and R makes it very easy. It's got the most powerful statistical techniques built into it. So why is R a good choice for this sort of stuff? Its capabilities, first of all, are similar to MATLAB, and I would say that if there has been one computing platform that has emerged among scientists and engineers, it is MATLAB. Not universal, but certainly more common than anything else. And it's very powerful. But R is free and open source, so anyone can afford it, download it, install it on your machine, learn it. It runs on all platforms. There are compiled binaries for all the common platforms. There is as we'll see, there are a wide variety of high-order functions that are built in, so you don't have to program Bessel functions or that sort, or solving for roots. I mean, things like integration of simple functions. Those are all in there. It's got excellent graphics, as I've said. And a very important thing, it's extendable and has been extensively extended by the user community with packages which are like MATLAB toolboxes. And in fact, there's sort of an embarrassment of riches here. There are currently, when I started learning R, there were under 3,000 packages. Now there are over 4,000 in about just a few years. Two of the packages, I think, or three of the packages are particularly important. The Pragma package translates many MATLAB functions into R. And so this is something that you really should, I think, download and just load in, just have readily available. And it uses MATLAB syntax as much as possible. Then the DE-solve and Reactran packages solve ordinary and partial differential equations, which is a lot of what we scientists do. It's an evolving platform, but a stable one. It has very regular 2 updates a year. And they usually don't break anything usually. They just tweak things a little bit. It's a full-fledged programming language with all of the standard programming constructs. It's interpreted, which means it's not as fast as Fortran or C or C++, but given the speed of modern computers that we all have on our desktops, unless you're dealing with very big problems with thousands of simultaneous equations or tens of thousands, it runs fast enough. It incorporates features of it is an object-oriented language at base, although you don't really need to know much about that unless you want to. For large projects where it gets unbearably slow, you can interface it to C or Fortran code for those difficult steps, and then use R for the input and output, which are not usually very gracefully handled by those lower level languages. It's a lot more efficient than a spreadsheet, I think, once you get used to using it. The installed base R has a lot of sample data sets that you can practice on, and a lot of online examples. As I've said, it's the program of choice for statisticians. So if you need statistical consulting, it gives you a shared vocabulary. In the bioinformatics community, there's a project that's sort of based at the Fred Hutchinson Cancer Research Institute in Seattle, called Bioconductor. And it is written in R. And it does very sophisticated, complicated things, handling very large data sets. At this point, I might mention that the R name, where that came from. The basic language in which R is written is a language called S. And S was written at Bell Labs. And it was given a one-letter name, I think, because C was also written at Bell Labs. And so C was for computing, and S was for statistics, or something like that. Bell Labs sold off S after a while. And so a company bought the rights to it, or part of the rights to it, and developed and put a graphic user interface on it and called it S+, and S+ still exists. But 2 guys at the University of Auckland in New Zealand decided to develop an open source version of S, and their names were Robert Gentleman and Ross Ihaka, both beginning with R, and so they decided to call the language R. Ihaka is still at the University of Auckland, as far as I'm aware. Gentleman went to the Hutch and led the Bioconductor project, and he's now in charge of computing at Genentech in the Bay Area. So that's sort of a historical background. Another very important thing is that there's a very active online community. So if you got a question about how to do something in R, you can submit a question. I mean, there's an R help website, and you will very rapidly get back a response. If you're not careful, the response will be read the effing manual. But if you're a little more thoughtful than that, you will get back an answer to your question. It's a grumpy community, but a helpful one. So what can you do with it? You can use it as a programmable graphic calculator. Imagine a TI-48 in your that you learned in high school, but with a lot more power. It's got a lot of graphic functions. It's just like MATLAB. Its basis is vectors and matrices. That's what it deals with most comfortably and most quickly. So a scalar is, you can do that, but you use it most efficiently if you've got a big vector of data or simulated numbers or a big matrix of them. That's what it's set up to do. It uses if, then, for, next, repeat, those if else, those kinds of constructs, the standard ones. It's got virtually every numeric capability you would want, and it doesn't have the symbolic toolbox that MATLAB does, or certainly not Mathematica, but it does have a set of symbolic manipulation functions for polynomials, which is pretty useful. And there is an interface, there's a freeware symbolic math program called YCAS. I forget what it is. Yet another computer algebra system or something like that. And there's an R interface, RYCAS, to that. So if you want to do symbolic manipulations, you can. It solves all the systems of linear and nonlinear equations that you would like it to. It has a lot of optimization functions, which a number of you have told me during the day-to-day is the nub of a lot of your work. Does numerical differentiation and integration, solves initial value and partial differential equations and boundary values. It'll do Monte Carlo simulations. It's got very powerful random number generation capabilities. And of course, it will do statistical analysis of data. This list of what you can do with R is basically the table of contents of the book that I'm trying to write now. So I just went through that. I haven't done the Monte Carlo simulations, but other than that, I've done at least a first draft of everything. 4,000 packages. Frankly, more than you need. And it's, I think, one of the weaknesses of the R environment, the R ecosystem, if you will, that there are maybe too many people out there writing their own code, putting it into packages, contributing it to the website, where it does get checked. But it's difficult to know just what's there and what the relative virtues of the various packages are. I thought I would just give you a subset of the of a few of the general classes of packages that would be of greatest interest to biological, physical scientists, MDs, and you can read this here. Now, I took just one of them, which is the differential equations task view. So let me go back here for a second. For each of these tasks, there is a curator, if you will, or a maintainer, who keeps up with the packages in that area and maintains an online commentary, a listing of them, and a sort of a brief commentary about what each of them does and their strengths and weaknesses. If you look at the differential equations task view, these are the subtopics. Each of these subtopics has several packages, but notice it's pretty complete. Stochastic differential equations, and we were talking earlier about what happens if you're trying to simulate differential equations with a lot of randomness in the system. Ordinary differential equations, delay differential equations, where you have a time lag between stimulus and response, partial differential equations, differential algebraic equations, where you say you have a set of chemical reactions, some of which are slow and some of which are at equilibrium, boundary value problems, and then other related packages. So, and this is probably the smallest of all the task views. If you look at the description of stochastic differential equations, there are 4 packages, each of which does things slightly differently. I don't have any experience with any of them except a little bit with the Gillespie SSA. And Gillespie's exact stochastic simulation algorithm is sort of the gold standard in this area. But there are approximate methods even there. So this is very rich. And as I said earlier, because it's a statistical language at base, does a lot of stuff with random numbers and probability. And it has, what is this, 7 times, it has 20 different probability distributions built in. And for each of them, you can call 4 things. The density, that is the value of the probability distribution at some given points, the distribution function, the integrated area under the curve. If you know the 90th percentile, what's the value at that point, the quartile function, and then the random number is drawn from that distribution. So if you have a physical model that involves, let's say, an exponential distribution or Poisson distribution or normal distribution, it's very easy to generate random numbers from that distribution. You just say R norm or R pois or something like that. So what I wanted to do now pretty much for the rest of this talk is to give you some very simple examples of, and I mean very simple for the most part, of how you use R to do more or less standard things. And most of these, in fact, are drawn from my blue book there. And one of them, the first one is root finding. That is to find the pH at which the net charge on a molecule is 0, so it doesn't move in an electric field. So in order to do that, you define, and I want to show you some code here. And I guess you can play along if you want to. I'm not going to run the. This is a PDF file, so I'm not going to actually run the R code, but you can if you want to. So you define a function. The FB is the fraction of base of that titratable molecule. It's a function of pH and of the pKa of the group, and from the Henderson-Hasselbalch equation, it is equal to that function of pH and pKa. And then the second function that you need is the given the state of titration, what's the net charge, Q net? And that's a function of the charge on the base, which in some cases would be -1, in other cases would be 0, and then of pH and pKa. So if we take just acetic acid as the simple example, we want to draw a titration curve, and so what are we doing here? We are telling them the first line, this par MF col equals C12, and is to say, okay, I'm going to want to, let me just jump ahead and show you. Whoops. I'm going to want to draw two graphs side by side. One of them I'm going to want to draw the fraction of base, and the other the net charge. And that's the kind of thing that a scientist often wants to do. I want to plot more than one graph at the same time. And the most common way of doing that in R is just to set the graphic parameter, par, and say, that actually should be MF row rather than MF column. MF row is C, which means C is a vector. Is the R term for a vector. Think of concatenate or combine two numbers, something like that. So one row and two columns is what C12 stands for. Okay, then I want to draw a curve, first of all, in the left-hand frame of the function of the base. Remember, the function of the base is up there at the top. It's a function of pH, which in this case we're calling X, and the pKa of acetic acid is 4.8. We want to draw it between pH 2 and pH 7. We want to give it the x-axis label it pH, and for the main title, the fraction base. Automatically, by default, the y-axis will be labeled FB. And one little point here is I can't. In the curve is an R function that plots a function, and that function has to be called X. It can't be called pH or Herman or whatever. And that's occasionally a nuisance, but not a big problem. Then I want to label the graph. I want to put text at coordinates 3 along the x-axis, the pH axis, and 0.8 along the fraction base axis. And I want to say pK equals 4.8. Then I want to add another, and in the second plot, I want to draw another curve of the net charge on the acetic acid. The basic form of acetic acid has a charge of -1. pH again is X, pK is 4.8 over the same range of pHs. I do the labeling here, and then I get the result that you've already seen. So that's how you do a simple. Yes, sir.
Just wondering what the left arrow and what was. Is that the comment?
Thank you. the left arrow I put in because I don't like to use it, and I put it in because it's the standard Arch syntax. But I wanted to give an example of how that's used and what you'll see. But from then on, I will use equal sign. Basically, that's a good symbol for assignment. So FB is assigned the value of the function. But every other programming language uses the equal sign.
So you could replace that with just equals?
Yes, yes. Yeah, thank you. I meant to say that and forgot. When that book uses equals, and when I contracted to do the book I'm working on now, I checked with the editor to say I want to use equals, is that okay? And I pointed out that Robert Gentleman, who is one of the co-inventors of R, in his most recent book uses equals. And so the editor wrote back, if Robert does it, I guess it's okay. And the referees have said it's okay too. So, you'll more often than not find this assignment operator, but it's just easier to use the equal sign. Okay, so here's a more complicated example. I won't go through it in as much detail. For glutamic acid, you've got really three titratable groups. You've got the alpha amino, the alpha carboxyl, and the side chain. And so each of those has a charge as a base. It's at a given pH, and it's got a pKa, and each of those is different. So here I've got the function now is the sum of those individual titration curves of the three units, but the calculation is just summing those together very, very easily. And so here's the result. And then another useful thing is this AB line, which is a convenient way of drawing straight lines. So, I mean, here it tells me or I tell it, to draw a line with 0 slope and 0 intercept. If I wanted to draw just a horizontal line, but maybe it's some other y value, I would say ab line h equals 0. If I wanted to draw it at y equals 3, I would say AB line v equals 3. The other thing, line type, LTY means line type. The default is a solid line, LTY equals 1. LTY equals 2 is dashed, L3 is dotted, and there are 3 other dot dash kinds of things. So you can customize the look of your graph. Okay, if I've got a peptide, and again here I'm overlooking the fact that in real biochemical life these charges would interact with each other, but if I just assume they're each separate, then the Q net on the molecule as a whole is a function of the pH of the charge on the base of each residue, which now is a vector, which you'll see in a minute. And the pKa is also a vector, and n is the number of each type of residue. We start out with the Q net equals 0, and then we just go along and add up the number of residues of type I, the function QB of residues of type I, and then the pH dependence of the titration of type I. Notice here the subscripts, pKa of type I and charge on the base of type I. And then each function returns a value. Now, if you don't put in an explicit return function, the function returns the last calculation in the function that's made. If you want to, and this would be okay in this case, because what I want is the final value of x. But sometimes you want a function value which involves several of the things that you calculated in the subroutine. Yeah.
So if we were worried about computation times, we would want to write this without a for loop, right?
Yes. And I guess you could just do it x equals sum
Right.
of all of that. Yes.
It might be faster.
It might be faster. For something, you know, I think for, unless you had a 10,000 amino acid polypeptide, you probably wouldn't notice the difference. But that's a good point. For something in which the terms in the sum don't depend on each other, on quantities of other indices, you can often write a vectorized expression which is much faster. Yeah, thanks for pointing that out. Yes, sir?
Does R have hashes or associative arrays?
Hashes.
They're sometimes called associative arrays where you have sort of a value, a key value.
Yeah.
A and then a value associated with A.
Yeah, I know what you're saying.
C
And you know, I haven't encountered that, but for the uses of R that I've seen, I wouldn't necessarily have encountered it. I know that Perl, for example, has hashes. And
Very powerful.
in that sense, I don't know. It may be that R does not. Does MATLAB have hashes? I don't.
Yes, called dictionaries.
Dictionaries. I don't know. R might well, and they might not call it hashes either. But I haven't encountered it in my explorations. Good question. So what we want then, then R has a function called uniroot, which basically takes an arbitrary function and finds it 0, where it passes through 0. So you don't have to program that. You just use the function uniroot. And so what we want to solve for 0 here is the function of QNet as a function of pH and these other things. And so when we write that, well, first of all, let's make up a peptide. What we've got here is something that starts with, that has a carboxyl and an amino group, and then some of these residues are charged and others are not. And so if we look at down the line here, these are the number of the charges on the basic forms of these amino acids, and then for the hexapeptide here, I've got 4 lysines, so I've got 4 side chains, and everything else is either 0. These are the charged amino acids or termini. I've got 1 of the C-terminal end, N-terminal end, no aspartic acids, and so on, and 4 lysines. So that's how one specifies that. And then I say draw the curve, as we've done before, and draw a line through 0. So what I want to do is to find that intersection right there. And when I use uniroot, that's what I get, 10.8 something or other. And I also get the information that the value of the function at the root is not quite 0, it's 10 to the minus 6th. Took 5 iterations to get there, and the estimated precision is 6 parts in 100,000. If you wanted just the uniroot itself without all this extra information, you would write uniroot $root. And then you would just get, because this is a list in R terms, and to pick out just a single component of a list, you put the name of the list, a $, and then the name of the component that you want. Is this more or less clear? Okay. Here's another example of the sort of problem you might be faced in analytical chemistry lab, or using spectroscopy on a solution to determine the concentrations of various components in a mixture. We assume that each of them has a Gaussian spectral shape given by an intensity, a maximum, a width, and a wavelength. And that's the expression for a Gaussian. And having defined that function, I define the assume I have 4 components in the mixture, and their spectra are functions specified, the functions of x specified by the maximum absorption, the wavelength of maximum absorption, the width at 1 over e, and so on. So for 4 of those. And then I have a vector, so I specify that my mixture has these concentrations in millimolar of each of the 4 components. And I say that I want to go over a wavelength range from 180 nanometers to 400 nanometers. And then I calculate a matrix which is has rows equal to the number of wavelengths and columns equal to the number of components, which is 4. And then I calculate a matrix AI1, which is 4, again, that number of rows and 4 columns equal to the values of those functions at each of the wavelengths. And I calculate the spectrum then over the wavelength, which would be the optical density, by matrix multiplying that matrix A into the vector, into the concentration vector. And the symbol for matrix multiplication, or multiplication of a matrix by a vector, is percent multiplication sign percent, which is once you have done it a couple of times, you remember it. And then you plot it, and notice how easy it is to plot. You plot OD as a function of x, which is wavelength. Make it a line, and that's what the spectrum looks like. Now, let us suppose that we don't know the concentrations, but we can measure the optical density at 4 wavelengths, and we want to get the concentrations, knowing the spectral properties of each of the 4 compounds at those wavelengths. And what I have done here, I think, got a little confused. I know a couple of you picked up and said this didn't quite work. It actually works here, but so if I make the measurements at 4 wavelengths, and I've got 4 unknown concentrations, I should be able to solve 4 equations in 4 unknowns. And basically, I'm not going to go through this in detail, but that's what this does. And so I've calculated that the measured optical densities at those 4 wavelengths should be have these values. And then, in order to get the concentrations, basically I solved there's a standard thing that you have to do in numerical analysis. I have a matrix A times an unknown vector x equals a known vector b. And so I want to solve ax equals b for x. And you do that by multiplying b by the inverse of a. And that gives you x. The way to do that in R is simply to write solve a b, where b is the optical density vector at those 4 wavelengths. And so I get these values. If I say round to 3 significant figures, then I get back the original concentrations that I put in. Now, any good analytical chemist would measure at more than 4 wavelengths, because if you can overdetermine your data, then you have a little more handle on the uncertainties in the system. The A matrix now, if I did it at 6 wavelengths rather than 4, the A matrix would no longer be square, and so I can't take the inverse. But what you can do, and this is standard in this kind of analysis, is to use a matrix technique called QR decomposition, which R has built in. And the problem here is that the way it was set up, A should be a 4x6, 6x4 matrix. Using the previous value of A, it was a 4x4 matrix. And so people got error messages who tried to simulate this. But if you went through the steps that I did before and just got the correct A matrix, you'd have a 6x4, and then QR would give you the right values, which again are the ones we started out with. So this all works nicely. Okay, now another common problem that people face in spectroscopy or any kind of a problem that involves exponential decays is fitting to a sum of exponentials. And there is fitting to arbitrary functions generally. And that's an optimization problem, or minimization of least squares, nonlinear minimization of least squares, something like that. R has a huge number of ways of doing this. Some of them built into the base, some of them in packages. The optimization task view in R has lots and lots of entries in it. What I did here was to take one example. The NIST, the National Institute of Standards and Technology, has a set of very difficult data sets that are very hard to fit. And so they're good tests for fitting routines like this. And I just tried one, which is which is a sum of 3 exponentials. And you'll notice that, that the decay constants are not very separate from each other. What I learned growing up is if the decay constants don't differ by a factor of 10, you're not going to be able to separate them. And so here you have 3 that are within a factor of 5 of each other. And so you can access you go to the NIST website and you can download this data file. This is the syntax for reading it into a table. You then import that table into R with an x-axis and a y-axis. And you plot it, and it looks pretty much like a single exponential, I mean, to the untutored eye. So, but if you use the NLS fit, the nonlinear least squares function, and you make some guess at the, I know what these values are. Now, that is, NIST gives you those values. The game is to try to get as close to them as you possibly using your own minimization routine. You write the fitting that you want to end up with, NLS LAN 3, is the NLS function of y depending on, this tilde thing sort of means depending on x. But here it's not, here it's 6 parameters, the pre-exponential factors and the exponential factors. So we got 6 unknowns here. These are the standard, these are the default parameters for doing the minimization. And in fact, if you just do it that way, the fit didn't converge. But if I changed I think I changed the min factor to 10 to the minus 8th or something like that, then what I got was these estimates. This is the table that that R provides. These triple dots means these are all significant to more than 3, p less than 0.001. And the original values were these. So I get 0.09, 0.09. This was 1, 0.95. For the decay constant, 2.95 instead of 3, 4.98 instead of 5. So very close, very close. Took 12 iterations to converge, a decent tolerance. And again, if I plot the data, this is the points are the data, the line is the fitting. These are the residuals, which look nicely randomly scattered. So this is a pretty terrific job of fitting a very difficult function. There are, I think, 10 such difficult data sets on that NIST website. I've tried 1 or 2 others, and they worked about as well. But this shows R's capabilities for doing this kind of thing. I'm going to finish up. I guess I'm running a little over time. Is that a problem with people? I can
Get some extra time into the schedule.
Yeah, all right. I'll try to move it along. The DE solve package is the basic one. You have to download it and add it to install it in the R system. Once it's there, you call it and use it forever and ever. And you want the ODE, ordinary differential equation, function in this package. And the usage is ODE is y, which is the initial values, the times over which you want to calculate, the function of the derivatives that you want, and parameters that feed into it, and then methods. And there are all sorts of methods here. The default is this LSODA, which is very highly developed Fortran solver of the same name. And one important thing is that it automatically switches between stiff and non-stiff sets of differential equations. You don't have to specify that. So that's very useful. But you've got, these are sort of the default ones, but you've also got Euler or fourth order Runge-Kutta or a bunch of the standard ones. These are pretty much the same as in MATLAB. All these routines come from LAPACS, which describes how this works, and I won't go into it. So what I did was to take the standard Lotka-Volterra predator-prey equation, a set of differential equations. You've got the variables here that you want to solve for as a function of time is collectively x is a vector in which you decompose into the prey constant, prey numbers and the predator numbers, and then you write the differential equations. The rate of change of prey is a product of predator and prey concentrations, but then a growth of the prey just due to birth. And the predator grows according to how many prey it catches, and it dies. The result that I want is these two derivatives of prey and predator with respect to time. And ODE says, feed me the list of those derivatives. And then I specify the times and the number of time steps and the parameters, the rate constants that are there, the initial values. And then I solve. I just write out equals ODE of the parameters. And if I need to, I give it some tolerances, which it has defaults for. So you see that I think this is very much like how MATLAB does it. And the results, as a function of time, the prey and predator populations oscillate in the standard way, and you get a phase plot of one versus the other that oscillates, repeats itself. And it all works very nicely. Now, I'm going to finish up the examples with so-called Brusselator reactions, which were designed by Prigogine and his group at what is the Free University in Brussels? I forget the name of it, but University of Brussels. And the idea was to devise a set of reactions that would lead to oscillating behavior. And so these are the reactants and products and the rate constants, converting them. And we're going to combine that with diffusion of the x1 and x2 reactants. A, B, and C, and D are reactants and products that are removed from the system. So X1 and X2 are the intermediates that matter here. So here we have a reaction diffusion problem. And we can solve that. We could write the code ab initio, but the reactran package, which we loaded with the library function, basically is designed to solve just that kind of reaction diffusion problem. We set up a grid, the number of divisions of this, in this case, one dimension, just the x-axis. We initialize the concentrations, and here we actually set up the x1 as a sinusoidal oscillation, and x2 as a constant, and so then we write the initial conditions and the differential equations. You'll notice here, because we have the chemical reaction steps here, these things, and then the translational diffusion, which is a bunch of code that you don't have to pay attention to, but which is written into the reactran software, into the reactran package for handling the diffusion part of reaction diffusion equations. And reactran not only has one-dimensional, but two-dimensional and three-dimensional variants, and not just in Cartesian coordinates, but in polar and spherical coordinates. And so we set the time interval, and we solve the set of differential equations. We also, you can, for calculations that may take a certain amount of time, you can use the system time function, which tells you how long it took to do the stuff here. And in this case, it took about 4/10 of a second to solve that set of equations on a MacBook Pro of a couple of years ago. And then to show you R's power in displaying the data in different ways, I'm going to do do 4 ways here: a 2x2 matrix of images, a contour plot, an image plot, which is sometimes known as a heat map, and 2 perspective plots, one colored and one not colored. And it basically just takes the out result, which is the result of doing that calculation, and it knows that the first vector, first column of the matrix output is the time, and then the others are the concentrations. And so here are the results of those 4 ways of plotting the data. Again, these are very comparable to the plots you'd see in MATLAB. I didn't want to write all the equations and go through this again, but this is an example of doing the brusselator in 2 dimensions, so you diffuse in 2 dimensions, and start with a random starting, so the concentrations initially are randomized for x1 and x2. Everything else is the same, and these are time snapshots at times 1, 2, 3, 4, 5, 6, 7, 8. How this evolves. So you can do reasonably fancy stuff. One of the I'm going to finish up in just a minute. As I said at the beginning, I think that scientists, at least in my acquaintance, tend to underestimate the utility of doing thoughtful analysis of their data, of doing statistical analysis of their data. And because R is so powerful in that direction, R enables you to access the data in various formats, clean it up, annotate it. Again, in the bioinformatics world, that's very important. Summarize it with descriptive statistics, visualize it, plot it, model it, and prepare the results for publication. And so my analyzing data chapter in this book that I'm writing does these various things. It goes through these, gives simple examples of how to do this kind of stuff. And it includes time series or spectrum analysis, principal component analysis, cluster analysis, things that are important for people that I've talked to today. So, to finish, come back to the question, why use R? Because it's free in both important senses. It's convenient, it's interactive, it's powerful, it's flexible, good graphics. It's got this very large and active and helpful user community. And to iterate again, it could be the basic quantitative statistical and graphics tool for most scientists and engineers. Thank you very much. I'd be happy to answer questions. Yes, sir.
You might want to mention, for people who are just starting to learn R, our commander gives you sort of a simple menu to do some of the really simple things.
Yes.
That makes it easier to kind of start, but you still need the control.
Yes, that's a good point. I've never used R Commander. There's another graphic user interface called RStudio, which I've used, but then sort of gave up and returned to. It's good, but
As soon as you know a lot more about it.
okay. But it basically, essentially, R is a command, as you've seen, it's sort of a command line interface. And essentially, you've got your coding window, you've got a graphics output window, you've got a help window. And if you hit the right combination of keys, you can get a listing of the variables that you've defined in the system. RStudio divides a big window up into 4 sub-windows, which gives you that information. So it may be easier sometimes to work with, and probably R Commando does something similar. Yep.
So you mentioned system timing. Does R have any sort of profiling facilities?
You certainly can apply system time to any part of the calculation that you're doing.
That's pretty much all it's got?
That's all I'm aware of.
Okay.
I don't know whether.
More than I was aware of.
4,000 packages though. So
Yeah, there's probably stuff in there that would, yeah. Yes.
When I was defining the package, I noticed that it had a TK TCL module or package. And if people used it to build more elaborate
You know, I don't know.
constructs,
I think if you,
sort of beyond the command line.
yeah, as far as I can tell, you know, the graphics that are, at least on the Mac that I use, you can do pretty much everything with either the built-in graphics or with graphics packages that you add. There are a couple of what is it, ggplot2 is a sort of a total rewrite of graphics in R. And then there's something called lattice, which is if you've got a lot of different variables and you want to see lots of plots of one against the other, so you can get a 5x5 matrix of small plots. So there are things like that, but You don't need to use TCL for that.
That would be more like putting a graphics interface on the package.
Yeah,
You can.
you can, yeah, you can do virtually anything, actually, but,
Well, there's
yeah.
some tools that would help you with, for example, our commander, there are about 20, 30 different ways that people have expanded it to solve certain types of
Okay,
problems. So
great.
When you put the time in, you can put a, and then there's some simple kind of graphics interfaces that you could put on to solve a single problem.
Okay.
I think, would be useful, obviously.
Okay, thank you.
Yeah, tools for converting between MATLAB and Dart?
Well, there is this Procma, which sort of uses MATLAB syntax to do certain things in R. There are cheat sheets, basically online small documents that give translation between most standard MATLAB commands and there are equivalents. Yes?
The one thing to mention, not to put down your book, because I think getting a finished book is a big advantage, but there's a lot of documentation on our website.
Absolutely.
They're like free books, or
Yeah.
things that develop into books.
And I'm glad.
That can get you started and have examples.
Yes.
I don't think they do as much of the type of thing you're talking about, which I think is a real plus to have a book in that area.
Yeah, thank you. I'm glad you mentioned that because I actually preloaded the R website where you can see things that are available. And here you have, down at the bottom of this page, you have manuals, you have FAQs, and you have contributed documentation. And if you look at the contributed documentation, just as one example, they divide it into English documents with more than 100 pages or less than 100 pages, and in Danish, in Czech, in French, in Parsi, in German, etc. So this is a worldwide community, and extremely helpful and extremely, let me see how we, I'm not used to this kind of a trackpad. But I just wanted to, I'm going to go back and just click on contributed again. Documents with fewer than 100 pages. Short documents and reference cards. Here's R and Octave, for example, which is a translator between R and MATLAB. R reference card. This thing by Tom Short is a pretty standard. It's in Chinese, but where was it? It's up here. A pretty standard short reference to a lot of the R functions. Here's R for biologists, which here's one on R Commander. So indeed, there are lots of free references available online, as well as a lot of books, most of which emphasize statistics, and I'm specifically trying not to do that in my book. But if you want to do statistics, this is Using R for Scientific Computing by Carleen Sotert. She's sort of the leader, I would say, in the scientific uses of R. Particularly, she's been the leader in developing the differential equations packages and so on. She's got a book on differential equations, which I saw on Dan's desk this morning. There are all sorts of approaches to R. that you can find online as well as printed books.
Well, thanks again.